radioactivity here. Basically, radioactivity involves the decay of large nuclei over time. And that may not be the exact definition that was given initially, but that's paraphrased effectively, I think. Why is it that large nuclei decay radioactively? I mean, what property is it that large nuclei have that makes them so unstable? Protons? Lots of them? So, if you imagine a uranium nucleus. Oh, you fine? I did it wrong. They should be closed circles.
You're a jerk.
I know, I forgot the little symbol all the way through. They'll close both circles, and then if they open them like I did, they should lose 2 points.
She hates you right
Capital H.
I can be game at home.
At least,
All this time.
I'm just admitting.
Yeah, right? No kidding.
I'm admitting fault in this thing.
He's not the only
He's on.
person who's excited for
Honesty is the
D&D.
best policy.
It is. So, large nuclei have many protons, and many protons means much repulsive force. So as the protons are wanting to get apart from each other, that's what makes the nuclei unstable. So this means we have an unstable nuclei. Now, when the nuclei decay from their instability, there are a few things that are naturally given off more often than others. So 3 common.
One more question, though. You don't have a number on, you don't have a points on here. Duh.
Right? That should be 8.
Okay.
So 3 common decay products are alpha particle.
Oh, you have 10, whoops. Oh, wait, never mind, I lied, it's just, don't. Sorry, guys, I'm all over the place.
Beta particle, which is an electron. Remember, that's kind of weird because you're getting an electron from a nucleus. But if you remember that a neutron is a proton plus an electron, that can resolve that problem in your head. And then C, gamma radiation, which is pure energy. Or a photon. All the stuff you should have in your notes, but this is, again, reviewing to make sure that we all are on the same page. Also, when we talk about the reactions that involve nuclear decay, if you start with a big nucleus and result in 2 smaller nuclei, this would be called fission. Breaking apart a big nuclei into 2 smaller nuclei. And if you went in the other direction, from 2 small nuclei to a big nuclei, that's called fusion. Fusion is the one that requires more energy to make the reaction happen. Fusion is also the reaction that gives off a huge amount of energy. If we could find a way to get fusion reactions occurring at room-like temperatures, that would solve every energy problem we've ever had. as a society.
Ooh,
Yeah,
cool.
it is cool. Because basically what you'd be able to do is have the energy of the sun being produced at temperatures approximately room temperature. That would be nice, because, well, to get energies like that of the sun, you have to get it really, really hot, which the amount of energy required to make it hot enough to have the fusion occur isn't worth it for the energy that you get back in return. But if we could get fusion occurring at room temperature like temperatures, we would convert very quickly all of our coal, nuclear, whatever reactors to become fusion reactors, and all the world's energy problems would be solved. The Earth Science book, which is from the 80s, lists in the back of it, it says, whenever it's, well, not in the back, but towards the end of it, whenever it's talking about fusion, it mentions that scientists hope to, by the year 2000, have cold fusion techniques. I always found that kind of comical, because every time we used the Earth Science book, it was always after the year 2000, and cold fusion is still something that seems unattainably advanced for now. Okay, let's check this out. What if we have this reaction? We start with polonium-218, and we form something plus an alpha particle. Now, we should be able to fill in the blank here based on the information that's given in the equation. Remember, the top number is the number of protons plus neutrons, and the bottom number is the number of protons. But regardless, on the left and right side, you should have an equal number of protons and neutrons. So if on the left we have 218 protons and neutrons, and on the right we only have 4 protons and neutrons accounted for, then the missing piece has to have 214 protons and neutrons. Essentially, the top numbers have to add together, so do the bottom. If we have 84 protons in our polonium, and only 2 protons are accounted for in the alpha particle, then we have to have 82 protons in whatever is left. Now, to determine its name, we're going to need the periodic table, because something with 82 protons has a particular chemical symbol associated with it. And if you go to the periodic table, element 82, lead, Pb. Where did I get that? From the periodic table. Bless
Let's
you.
see, huh?
So there's the link there. The number of protons is going to tell you the identity of the substance missing. What about this guy? From 21482 lead, we make 21483 bismuth and something else. So these are simple nuclear reactions. Basically, fill in the blank. Can you work backwards to figure out what's missing? So notice, in this situation, the number of protons and neutrons are the same in both cases, right? So there's no protons and neutrons to account for. All protons and neutrons have already been accounted for. We have 82 protons on the left, 83 protons on the right. So what number is going to have to be down here? Yep, -1. And 0, -1, the way that my mind thinks of this, the way that I think is a decent way to think about it is, if you have the opposite of a proton, you have something that's the opposite of a positively charged particle. In other words, you have a negatively charged particle, an electron. A nice follow-up question to this would be, what type of particle is that? Question mark. That would be a beta particle? Yeah, that would be a reasonable question to ask. Another reasonable thing to ask, or another reasonable thing to ask if you would be to say, what is the reaction for decay of uranium 238. So in this case, I would be telling you that there's alpha decay, that there's an alpha particle being given off from this nucleus as this nucleus starts to break down. And I'm also telling you that the thing that you start with is uranium-238. Well, going to the periodic table for uranium, uranium has 92 protons. So to start the reaction, we have uranium-238, and it undergoes alpha decay. You have to know what an alpha particle is to be able to pull this off. An alpha particle is a helium nucleus, 4,2 helium. And then there's got to be something else as well, because when the alpha particle is given off, something will be left behind. Well, if the alpha particle accounts for 4 of the protons and neutrons, there's going to be 234 protons and neutrons in the remaining particle. And if the helium particle accounts for 2 of the protons, then of the 92 protons that were in the uranium, now 90 will be present in the other nucleus. And then you say, well, what is element 90? You go to the periodic table. TH. Nice. Thank you. Thorium. And you really don't even have to know what thorium's name is. You just have to write TH. But you start with what we start with, and then involve an alpha particle in the decay, and you can produce the whole reaction from scratch. That'll be fine. No, that's yeah. I'm not sure what that was thinking there. Oh yes, something else to keep in mind. Whether it be a fission reaction or whether it be a fusion reaction, in either case, there's going to be some sort of energy release. In any of these types of reactions, there's going to be some energy given off as a result. And the energy that's released as a result of fission and fusion reactions is expressed by Einstein's famous equation E equals mc squared. Recall last time we gave an example looking at a particular reaction. And what we did was we compared the mass of what we started with the mass of what we ended with. And I'll just tell you straight out here, if we were to compare the mass of the reactants with the mass of the products, the mass of the reactants with the mass of the products, I'll tell you right now, in any nuclear reaction, the mass of the reactants is going to be greater than the mass of the products. What you start with is always going to be greater in mass than what you ended with, and it's going to be greater only by a very small amount. But remember, a small difference in mass will lead to very large releases of energy. Even a very small difference in mass leads to a large release of energy. There was a famous experiment that was done back in the day. This would have been hundreds of years ago, but imagine this experiment for a second. That's not drawn to scale, obviously, but the sun is giving off lots of energy all the time. And what someone did was they took a chunk of ice and they put the ice cube or the ice chunk out to melt by way of the sun. So the sun is beaming down on this chunk of ice, and the chunk of ice is warming up as a result, and eventually turns into liquid. Now, you can measure, because the ice is water, and because when water changes temperature, degree by degree, you can measure the amount of energy in calories very easily. Remember, a calorie is the amount of energy required to increase the temperature of a gram of water by 1 degree Celsius. So imagine you had a 10 gram mass of ice, and imagine it goes from 0 degrees Celsius to 20 degrees Celsius. Well, you can measure exactly how many calories of energy that is. For that matter, you can measure exactly, depending on how big your ice cube was, you can measure exactly how much of the sun's path of rays you were catching. Because the sun's rays are actually going in every direction, both, you know, in all 3 dimensions and everywhere. So you can measure as well, based on where you are at Earth, how much, what percentage of the sun's rays you were catching. Because if you just look at the surface in Earth's distance away from the sun, there's a big surface that would be able to catch all of the sun's rays if you had the sun sort of contained, if you thought of the sun as being contained. And you would be getting a small amount of it. Well, you could determine the percentage of the sun's rays that you were catching. You can determine the number of calories of energy that came within that percentage of real estate of the cosmos. And then you can backtrack and say, well, then how much energy is the sun producing at any moment in time? And backtrack one step further using this equation to determine what mass of the sun is being consumed every second. And the person who did this experiment was able to get it within like 10% of modern estimates back 100 years ago. And the neat thing about it is we can see exactly how much mass of the sun is being consumed every second as a result of the sun going through its processes. The experiment that I just described is something that would be able to be done by a high school student today. I mean, it's not a very challenging experiment. Figure out the area of the ice cube, figure out the area along the surface of a sphere in Earth's distance away from the sun, figure out what percentage of the sun's rays you're then catching, figure out how much energy you're catching, scale it up to figure out how much energy the sun is producing, work backwards to figure out how much mass that would be consuming. The ideas that are present there are ideas that are on display in this chapter. Small amounts of mass loss, huge amount of energy. I don't recall exactly the numbers that we came up with the other day, but we lost like 0.01 grams of mass, and we made like a billion times more energy than an electric blanket. I think that's kind of incredible. Anyone have any questions? One thing I'm forgetting here is the phrase chain reaction. One of the attributes of a chain reaction is that one of the reactants is also a product of the reaction. Remember, in the case of the atomic bomb reaction that we talked about, one of the reactants is the little neutron that's going to strike the uranium atom. Remember? So whenever you start the reaction, you start the reaction with a neutron and uranium. And the uranium will break into a couple things, but one of the things that you produce as a result is more neutrons. So you start with one neutron, and then the uranium atom breaks into krypton and barium, and you give off 3 neutrons. So notice one of the reactants one of the things that you start with, is also one of the things that's given off as a product, allowing a future reaction to occur. So long as any of these three neutrons strike a uranium nucleus, if they find a uranium nucleus nearby, then they will make that uranium nucleus unstable enough to break apart into krypton and barium, in which case 3 more neutrons are given off to find 3 more uranium atoms, to make those uranium atoms unstable, to break those uranium atoms apart, to then give off 3 more neutrons. It's kind of a domino effect, if you will. When one domino falls, it allows another domino to fall, because the act of the domino falling keeps all the dominoes moving. So the act of the neutron both starting the reaction and coming out of the reaction, now you have reaction starters coming out of the very reaction that was started. That's kind of a unique little reaction. So any reaction of that type, in general, we call a chain reaction. One of the things you start with is also one of the things that results from the reaction. You can almost think of this like throwing a match on a fire, and then whenever the fire's done, it gives you 3 matches back in return. Right? It's almost that absurd. But it's kind of neat, right? Any questions? When we went through the fill-in-the-blank problems, was that understandable? Not a problem? Good. So just a reminder, Monday, we'll have a quiz. It'll cover chapter 31, it'll also cover chapters 20 and 21, which chapters 20 and 21 had a few ideas. Enthalpy, which was keeping track of heat energy. We call that delta H. Remember, if delta H is negative, we have products with less heat energy, we have more stable products, lower energy products, and that's preferred. Delta H, negative delta H is preferred. Remember, we also talked about entropy, measure of disorder. In addition, we talked about kinetics, we talked about equilibrium, and we talked about Gibbs free energy. So those are the 5 real big sticking points from those chapters. Make sure you have a concept of those things come Monday.
Thank you.
You're welcome. You're welcome. Let's do all that, please.
Well, you're done. Thank you. Thank you.
B of some sort.
I know, like,
Okay,
So yeah, really good. 2 A pluses.
okay.
like he's like asleep.
The ones that are in the class, I showed them the grades.
Okay.
I